Hey everyone, my name is Liu Hao. I'm coming from the USTC, and I'm here to make the presentation about the papers, which the title is Multi-User MISO with Stack Intelligent Metasurfaces, a DRL-based sound-rate optimization approach. And this paper has published in the EEE TCNs. And I will introduce this paper in its 6 sections. The first is the background. What is the SIM? SIM, the full name is Stack Intelligent Metasurfaces. It achieves artificial intelligence via a physical neural network structure in the wave domain. And the SIM has the potential to supplant baseband beamforming the point-to-point communication systems, enabling wave-based beamforming in real time. And the Figure 1 and Figure 2 shows 2 different SIM prototypes in 2 different papers. And in typical neural networks, the issue of multi-user interference considered a significant obstacle that considerably decreased the system performance. This was an advancement in diverse interference management techniques. For example, the alternating the optimizations. This optimization technique makes the system instability caused by the high sensitivity to initial conditions and parameters. It also decomposes the joint optimization into sub-problems, makes the solution problem to converging to local optimal. So we consider the deep reinforcement learning to optimization SIM in this kind of systems, because it's a dynamically adjustment to evolving environments and task-enabling generalizations. And it's also exploring the neural networks for robust feature extractions. And then I will introduce the system models and problem formulations. The figures 3 shows consider the same added multi-user MISO transmission systems, and we can see that the beamforming is performed by the SIM in the wave domain. Because it reduces the number of radio frequency chains, enable low-resolution digital to analog converters, and the controller, for example, the FPGAs, turns the phase shift of the SIM in the real time. Because it makes the system adaptability to the wireless environment and enable self-learning from system feedbacks. And then the equation 1 and 2 shows the multi-layer structure of the SIM. And as we can see, the SIM is stacked structures made by a multi Metasurfaces, and the equation 3 shows the interlayer propagation parameters, which is come from the radius Sommerfeld diffractions equations. And then the main matrix is derived from the SNR at each user equipment. It explores expressions as the equation 4, and the objective of the papers is to maximize the system's sound rate performance, and the variable we have to optimize is the SIM phase shifts and the transmit power allocation vectors, and the P1 shows optimization problems specifically. And then we will introduce the proposed DRL design. Specifically, we use the DDPG algorithms as chosen DRL algorithms here because it's well suited for these scenarios. For its continuous action space, compresses a continuous action space and has a stable learning processing. And the figure 4 shows the DDPG structures in this papers. The agent is a continuous interact with the environment, which is the same as it in the multi-user wireless communication systems. And here below is the action states and reward we choose in these papers. Action is, of course, we choose the optimization variables in these papers, the SIM phase shift and the transmit power allocations, and the states is made by the last time step rewards, last time step actions, and the current channel states informations. And the reward, of course, we choose the optimization objective in this paper. And here we choose the network architectures in these papers. Is shown in Figure 5. There are two kind of different network architectures, which are the actor network, critical network. The actor network input the state vectors, generate the action vectors. Of course, they generate the same phase shift and transmit power allocation strategies, and we combine them into vectors. The vectors then go through the writing processing and applied to the environment, and in other way to go through feed into the creating network. The creating network input the state vector and the action vector to generate the Q value. The Q value is to evaluate the action vectors from the actor networks. Then we consider with simulation results. Here we choose the simulation setup in this slide, and we consider the scenario setup and the same configurations parameters. And the Figure 6 shows a simulated SIM SSD to user Metasurfaces. Specifically, the Figure 7 shows the average sound rate versus the transmit power for SIM SSD scheme, considering 4 transmit antennas, 4 metasurfaces, and the 81 metaheads on each metasurface. And we can see that the joint optimization of the SIM phase shift and transmit power allocations for DRL schemes effectively harness the inter-user interference compared to DRL-UPA. The UPA means the uniform transmit power allocations. The sound rate of the DRL grows faster with the increase of the transmit power, benefiting from inefficient power allocation strategies. And Figure 8 shows the average sound rate versus the number of transmitter antennas for different techniques, where we consider the hybrid precoding schemes and MMSE precoding schemes. And we can see that the same SSD, the interference cancellation scheme, eliminates the need for digital precoding and BS. And also, all digital systems require 35 transmit antennas to surpass the performance of same assisted systems with 4 transmit antennas, when we considering 49 low-cost metaheads on each layers. And the Figure 9 shows the average sound rate versus the number of Metasurfaces, considering different transmit powers, and 4 transmit antennas and 49 meters on each metasurfaces. The initial improvement springs from the enhanced interference mitigation and precoding capabilities offered by the multi-layer SIM structures, and the same performance eventually storages due to the fact that the optimization of extensive parameters become intractable. The Figure 10 shows the convergence behaviors of the average sound rate under different parameters of the writing process. The whitening process leads to a smoother DRL training process because it simulates the uncertain in real wireless communication environments, and thus makes the trained model of robots to uncharged interference. The whitening process has the effect of regularization, but it requires to control the parameter carefully. Then lastly is the conclusion. Here a joint optimization framework of the same phase shift and transmit power allocation aimed to maximize the sound rate performance was formulated. A same approach operating on continuous value solutions, and the result labeled data was proposed. The same phase shift and the power allocation strategies were directly extracted from the DRL's actor network. The presented simulation results validated the efficiency of the SIM for multi-user interference suppression, particularly under low transmit power levels. The proposed DRL optimization output the state-of-the-art alternating optimization algorithms. Then we choose the part of the reference of the papers. Here, if anyone are interested in the papers, you can find the specific papers in their journals. And that's all on my presentation. Thanks.